So we are doing a recap on chapter 9. Okay, so I'm not going to cover everything, but apa yang penting je lah. Kita sekarang ni, we are currently learning about oscillation and also about waves. So the first part of this chapter is about oscillation, right? Oscillation is repetitive over the same path. Okay, we already talked about it yesterday. Repetitive and same path. Okay, and waves is repetitive but moves forward. But moves, okay, moves forward, backwards, doesn't matter lah. Forward or backwards. So here, waves ni dia berbeza dari oscillation because it moves. Oscillation is repetitive over the same path. Okay, to the first thing that you must remember. Okay. Now, a simple harmonic motion is a type of oscillation or the repetitive over the same path. So simple harmonic motion is repetitive over the same path. Simple harmonic motion ada several types of systems such as the horizontal spring system, horizontal mass spring system. It's called mass spring because you have a mass over here and you have a spring. And this is called the vertical mass spring system, and this is called the pendulum. Okay, these are all simple harmonic motion. Why am I not visible? Okay, I should. Okay, sebab saya tengah semangat. Okay, never mind. Bising lah. Kejap. Sekejap. Too much. Okay, so anak saya pun tengah semangat sebab saya semangat. Apa-apa sajalah. Okay, so simple harmonic motion, kita ada horizontal mass spring, we have the vertical mass spring, we also have the pendulum. Okay, these are all simple harmonic motion which is repetitive over the same path, right? Okay, so moving on. And I told you that a circular motion, a ball in a uniform circular motion, is also a simple harmonic motion when you map the displacement on one dimension. Mapping its displacement onto one dimension. Okay, one dimension maksudnya either its x-axis or y-axis will show you that it is also a simple harmonic motion. One dimension shows that it is a session, right? It's a repetitive over the same path. And we can look at here, over here, it is repetitive, yes. It is also over the same path. So it satisfies both repetitive and over the same path. Now, one thing that we must remember is that when we map this circular motion onto one dimension, abaikan background noise too, we can see that it oscillates from positive amplitude to negative amplitude. Sama macam a spring, right? And the amplitude is the maximum displacement, right? So amplitude is max displacement. Okay, so that is I forgot to tell you, amplitude is maximum displacement. So in this case, our maximum displacement or our amplitude is actually the radius. So amplitude is actually radius in this case. Okay, because why? It's the same, right? This is also A. This is R equals to A, radius equals to A lah. Okay, so when you map a uniform circular motion onto one-dimensional axis, you can see that it is a simple harmonic motion because it is repetitive over the same path. Now remember, kita belajar in chapter 6 that a uniform circular motion has two dimensions, right? Because, dia ada two dimensions lah because it has an angle. That is why when we break it down into one dimension, we can see that it is actually simple harmonic motion. Kita kena break down lah sebab dia dual axis. Okay, so we can actually, I already wrote it here. Okay, so A equals to radius. A is also equals to radius over here. A is also equal to radius over here. Uniform circular motion that is projected onto one dimension is simple harmonic motion. And the period T is the time taken to complete one cycle. What is one cycle? If you start at this point, you come back to this point. That is one cycle. You come back again, 2 cycle. Come back again, 3 cycle, and so on. Okay, moving on. And then we learned about frequency. Frequency is 1 over period. It is the number of complete cycles per unit time. Okay, so frequency can also be, frequency is related to omega, right? Omega, angular speed by 2 pi f or 2 pi over t. Okay, so this is an important equation that we will use over and over again in this chapter. And the units for omega is radians per second. Okay, so basically it's the speed of this rotation. Okay, the speed of this rotation, that is your omega. And then we discovered that we can, Yusuf, slow it down, please. Slow it down. Mommy's teaching. Okay. Okay, so we discovered that simple harmonic motion, it has a sinusoidal nature, which means that we can mathematically represent it using equations, right? So for the y displacement, we have this equation, y equals to amplitude sine omega t. And the x displacement is amplitude cosine omega t. Remember, this equation shows you displacement. Okay, which means that we also can find velocity and acceleration, which is our next slide. No, this is not the slide. Okay, this one is the slide. And we also differentiated our displacement equation to give us the velocity and acceleration. Okay, so I don't think I have to go over this again. So x is a cosine omega t. This guy becomes negative, and we also have negative here. This is for x. For y, it's a sine. Remember, sine is for y. And then the velocity is positive. Compared to x tadi, it's negative. Ini positive. Okay, positive. This guy is negative. Okay, so please remember. And then we also learned that we have maximums. Okay, let me show you the slide. So from this graph, we can see that the maximum for x occurs at a. So the maximum x is a. And for this graph, when we plot it, we can see that the maximum happens at omega a. I mean, it doesn't happen there. It gives you the value. It happens at t over something. What? I don't know. T something, right? It happens at times something something. And the amplitude is omega a. So that is your equation. And the maximum acceleration, sama juga, we look at the positive amplitude of the equation, which is this guy. Positive amplitude of the equation. Positive amplitude of the equation. Positive amplitude of the equation gives you the maximum. Okay? If you don't want to memorize the maximum, you look at the equation. What is the maximum amplitude? That is your, what is the positive maximum amplitude? Positive maximum amplitude is your maximum lah. Is your max value. Okay, that is something very, very important. Okay, please remember that. Okay, and then I believe you know this one. You just have to plug in your t equals to what is the time that you want, and then you plot it. This is basically plotting lah. Okay, nanti kita akan buat example where we plot this. Okay, later on. But this one ada dalam module, I believe. So please take a look at that. Okay, we already did this problem. I will also record this problem again for those of you yang blur. I intend to record all the problems together in one lecture. So I will be skipping the problem examples for now. Kita akan continue with lecture dulu. Alright, so now dah habis recap tadi. So kita sambung with a new topic. Simple harmonic motion of mass spring system. Tadi kita cakap pasal equation and how it looks like on one dimension. We talked about velocity and we talked about acceleration. Now we are talking about the mass spring system. So the mass spring system is given by this equation. Force equals to minus kx. We have seen this equation for your chapter on energy, I believe we derived it. We derived it to get your 1/2 kx squared. But this is force, This is force, and it has a negative sign because it is a restoring force. And we already discussed what is restoring force. It basically means the system. Okay, abaikan. The system always wants to go back to equilibrium. To equilibrium. Okay, sebab dia sayang sangat nak balik rumah. Okay, so saya tarik dia tak nak balik rumah. Saya tarik dia tak nak balik rumah. Saya compress pun dia nak balik rumah juga. Di rumah dia equilibrium dia lah. Okay, so that is what a spring mass does. It has the restoring force that always wants to go back to equilibrium. So the negative sign shows that if I displace my spring, maksudnya saya stretch to the right, If I stretch to the right, my force, the spring, the spring's force will go to the left. How do I know this? Because when I stretch it to the right, I have positive x. I substitute my positive x into this equation, I get negative force, which means that my force is this way. The spring force, abaikan yang ni. Right? Sama juga when I compress it. Oh sorry, yang ni sebenarnya compression. Tak nampak. Okay, so maksudnya I am compressing. Okay, maksudnya saya negative x, right? So kalau masuk dalam equation ni, okay, saya cakap negative d lah, negative d, supaya tak confuse. So saya akan compress, maksudnya displacement of the spring is negative d, right? F equals to minus k negative t. So this gives me a positive F, right? Positive F maksudnya the spring goes to the right. Okay, sama juga macam saya stretch. What sound is that? Okay, sama juga macam saya stretch. This is me, mana stretching? Okay, this is stretching. Okay, so stretching gives me positive D. I stretch it. Okay, tadi tu saya compress. Okay. Okay, and then when my D is positive, my F equals to minus KX is minus KT, right? So my F is negative. Maksudnya, my F as my spring force will go to the left, right? So that is the restoring force. Little recap for you there. Kita panjang pula recap ni. Okay. So, macam mana kita nak relatekan that force with simple harmonic motion? Kita cakap simple harmonic motion is repetitive over the same path. And we know that the V is minus omega x. And our x is it's A cosine omega t, right? Apa saya tulis ni? So this guy becomes A sine omega t. And this is the acceleration. So this is the equation that we discovered mathematically for simple harmonic motion. Sekarang ni kita nak relate to the mass spring system because kita claim that the spring is a simple harmonic motion. So how do we relate these two together? So now F equals to MA, right? F is also equal to minus KX. So if I were to substitute this equation that we derived for simple harmonic motion into my F equals to MA, I will get this equation, right? F equals to M minus omega squared X. So sama. Saya akan dapat negative M omega squared X, right? And okay, bear with me, kita baru dapat equation ni. So saya baru substitute. Apa yang saya buat? Saya substitute equation A, acceleration into the MA. Untuk cuba relatekan. Okay, so next. Now that we have two equations, we have the restoring force equation for the mass spring system. And we also we substitute our acceleration from SHM into our Newton's second law, right? The basic equation for force. Kita nak cuba relatekan. And then we equate these two equations together, right? So let me do it up here. Kx minus m omega squared x, right? So x cancels out. So the positive also cancels out, right? So km, if I want to solve for omega, this guy becomes like that. So square root of k over m from these two equations. Okay, these two equations relate the restoring force of the mass spring system, relates the Newton's second law, and also relates the mathematical expression for acceleration for a simple harmonic motion. So ada tiga equation, kita dah mix them up together. What do we get? We get the angular frequency or the angular speed. Angular frequency or speed sama juga maksud dia for a spring mass system. Okay, so this is what we get, the angular speed or the angular frequency of a spring mass system. And we know that omega is 2 pi f or 2 pi over t. So from this equation, you can just memorize this one and relate it back to this guy to get your t or to get your f. Okay, substitute, rearrange, you will get it. Sama, you will get your t, you will get your f. The basic equation that I want you to remember is this guy over here. If you still can't remember, you derive lah. Okay, ni lagi susah lah. I suggest you to memorize it lah because it's very simple. Omega equals to square root of k over m. What is k? K is the spring constant. M is the mass. Okay, k is the spring constant. K is the spring constant. And m is the mass. Okay, from this equation, you relate back to your omega equals to 2 pi f or 2 pi over t. You can get your t equation and your f equation, frequency. Okay. And another thing that I forgot to mention, for a simple harmonic motion, your f, to satisfy the simple harmonic motion, these are the two conditions for your force. Okay, kalau ditanya, what is the condition for a force in a simple harmonic motion system? So this is the answer. It must be proportional to displacement. It must be opposite direction to displacement. If you can't remember these two sentences, I suggest you to remember this equation. So what is it? It is opposite to displacement, right? Because we have the negative. And it is also proportional because f is proportional to x. Okay, so this guy is proportional because minus k is just a constant. Okay, that is what it means by proportional. Kalau f saya increase, x saya pun increase. Kalau x saya increase, f saya pun increase. Vice versa. That is what proportional means. Okay, kalau decrease pun decrease, f decrease juga. Okay, so banyak pula bebel pasal ni. Okay, so this is your very important equation, omega equals to square root of k over m. Okay, so now, tadi tu kita belajar pasal the frequency, the angular frequency of a spring mass system. Now we are learning about the energy of a spring mass system. Okay, physics loves energy. So, kita memang akan ada energy in every topic, okay? So, potential energy of a spring. Kita dah belajar ni. It's 1/2 kx squared. Nasib baik saya ada screen ni. My kid is like jumping on the bed right now. Okay, so. Okay, potential energy of a spring is given by 1/2 kx squared. Right? And we know that Ke, our kinetic energy, is 1/2 mv squared. So, the total energy, because when you have a spring, it moves back and forth. It also has potential energy. So ada Ke, ada Pe as well. So you have both of this. So the total energy for a spring mass system is E Ke plus Pe. The total mechanical energy will be conserved as we are assuming that the system is frictionless. So your problems should be simplified lah when you don't have friction. Kalau ada friction memang saya pun macam Sesak nafas juga nak jawab. Okay. So total energy is equal to kinetic plus potential, right? Okay, so let's talk about the situation. Do I have a picture to show that better? Sekejap Okay, itu dah jauh dah. Bising lah budak ni. Okay. Kita nak pakai gambar ni lah. Okay, so let's talk about the energy in this diagram, in this figure. Macam over sangat terlebih ceria tu. Saja je. Okay, okay, so let's talk about the PE and the KE of a spring mass system. Spring. Huh?
What's a mushroom?
What's a mushroom?
Please. I don't want mushroom. What's mushroom?
Yeah. Budak ni. Okay, he's gone. Good. Okay. Okay. Okay, so when I stretch it, right? When I compress it, kita start with compress dulu So when I compress it, I am actually giving it the maximum PE, potential energy. Okay, I'm going to repeat myself. When I compress it or stretch it, okay, when I compress it or stretch it, so this is stretching, I am giving maximum PE. Maximum PE. Why? Because that is the maximum amplitude that I can give. When I compress it, I'm giving it the maximum displacement. When I'm stretching it, I'm giving it the maximum displacement. How does that relate to PE? PE is equal to 1/2 kx squared. The bigger your x, the bigger your PE. Now, when I compress it, I'm giving it the maximum displacement because that is my amplitude, right? So that means my PE is at the maximum when I compress, when I stretch, right? Okay. So this is maximum PE. What is the kinetic energy when I compress it or when I stretch it? Is it moving? No, it is not moving because it is temporarily on hold, right? So at this point, when my PE is at the maximum, my KE is equal to 0. Okay, and again, when I stretch it, it is on hold sekejap. Maximum PE equals to maximum PE is also when KE is equal to 0. Okay, so let me write that somewhere else. So PE is equal to 1/2 kx squared, right? So PE is proportional to x squared. So kalau kita kasih dia maximum displacement, kita punya PE pun jadi maximum. Okay. So tu bila kita compress and bila kita stretch. Now when I release it, it will have some speed, right? I release it, dia pergi equilibrium balik, right? So what happens? When it reaches the equilibrium, so let's say this is our equilibrium. Okay, because displacement is equal to 0 over here, what happens? When my spring reaches this particular point, the equilibrium, my PE is equal to 0. Sebab displacement is 0. Look back at your equation. When x is equal to 0, PE is also equal to 0. But what happens to the kinetic energy? This is when your KE is maximum. When it is at the equilibrium, right? And then, saya compress, lepas tu dia, mula saya compress ke sini. Lepas tu dia akan pergi balik ke equilibrium, right? So PE equals to 0, KE equals to max. Lepas tu dia akan pergi ke, sebab dia akan rotate, right? Dia akan oscillate from negative A to A, right? So this is your negative A and this is your positive A. Dia akan pergi ke hujung sana pula. So when dia pergi ke hujung sana, it is when it is stretched. Okay, bukan. Ini bukan stretching. Stretching is down here. So this is your positive A. This is your positive A and this is your negative A. Where's the compression? This is the compression, negative A. Okay. Okay, so when I compress, it is at negative A displacement. When I stretch it, it is at positive A displacement. When I compress and when I stretch, it gives me it gives me potential energy yang paling maximum. Okay, and then bila dia patah balik ke equilibrium, when I compress it, it wants to go back to equilibrium, right? Go back to equilibrium. And at this point, at equilibrium point, PE is equal to 0, KE is the maximum. And then, dia akan pergi ke sana lagi, dia sambung perjalanan dia, tak habis lagi perjalanan dia, dia akan pergi ke positive A, which is down here. Okay, dia akan pergi ke positive A. And then this is similar to how it is stretched, right? So when it is here, it gives me the positive A, it also gives me PE maximum. What happens here? KE is also equal to 0. Lepas tu dia patah balik sebab this simple harmonic motion. It repeats positive A, negative A, positive A, negative A. Each time dia sampai ke positive A, PE maximum, KE 0. Sampai balik equilibrium, PE kosong, KE maximum. Pergi balik negative A, PE maximum, KE kosong. It happens over and over and over and over again. Right, so if you understood that part, we will look at this equation now. So to represent this mathematically lah, apa yang berlaku bila KE turun naik, PE pun turun naik. This is the equation. It is dependent on the displacement. E is conserved, maksudnya dia akan constant. So kalau KX turun, MV naik. Kalau KX naik, MV turun. Kalau ni jadi max, ni jadi kosong. Kalau ni jadi maximum, ni jadi kosong. Because of conservation of energy. Okay, faham eh? If you have questions, this is the right time to ask. Okay. Okay, so tengok graf ni pula. Okay, sorry, saya nak tengok equation ni dulu. I told you when KE is maximum, when KE is maximum, PE is 0. So this is what happens to the equation. E equals to 1/2 MV max. Sebab apa? Sebab PE sekarang dah jadi kosong. So kita boleh terus cakap, okay, E at a certain point becomes 1/2 MV max. Bila dia berlaku? Dekat equilibrium. Tapi jangan cakap waktu dia belum start perjalanan, dia belum start oscillation lagi, dah cakap, oh, E equals to 1/2 MV max. Tak boleh lah. Dia kena start dulu, oscillation dia dulu, baru dia dapat E equals to 1/2 MV max at the equilibrium. At the equilibrium. Okay. Sebenarnya saya suka spring mass system ni because it's very fun in my opinion. Okay. And then kita dah cakap, bila kita punya PE is maximum, our KE becomes 0 sebab dia akan stop sekejap. Bila dia ke hujung sana, dia stop sekejap. Ke hujung sini, dia stop sekejap. Baru dia teruskan perjalanan kan. You can try this with your spring. You can see that it will momentarily stop when it reaches the maximum displacement. So, bila itu berlaku, kita boleh tulis balik equation ni. KE, so KE dah jadi 0 kan? So your 1/2 KX squared ni dah jadi A because that is your maximum displacement. A is maximum displacement. Okay, so that is why you have these two equations. Okay, now let me repeat myself. Yang ni bila dalam tengah perjalanan. We use this equation bila kita tak tahu if it's at the, kita guna equation ni bila dia bukan di equilibrium and bukan di maximum ataupun the negative A. Okay, do not use this. Okay, bukan do not use this lah. Use this equation, right, when not at max A, max or minimum A, and not in equilibrium. Not at, bukan in. Equilibrium. Lagi dia nak eja. Okay, use this equation bila you are not at the equilibrium, when you are not at the maximum displacement, either positive or negative. Use this equation when you know that you are at the equilibrium. You know that KE is maximum, so that is your equation. This is at equilibrium. Okay, pandai-pandailah faham tu equilibrium. And this is when you are at the maximum displacement. Tak kisahlah positif ataupun negatif. And this is at the A. Okay, so kita dah ada 3 equation. Okay, wait, kita ada 3 equation ni. So now we can equate them. Okay, so we know that the total energy is conserved. Okay, total energy is conserved. Maksudnya, this guy over here is equal to this guy over here.
Mommy, can Mommy boy?
Okay, give me the phone. Okay, so that kita equate these two together because we know that the value is the same because energy is constant. Okay, so now I can solve for V max equals to K over M A. This is how I get the equation. Okay, buang 1 over 2, buang 1 over 2, and then K A squared over M, and then you want to solve for V max. V max equals to square root of that. Your A ada square, so that becomes K over M square root A. Okay. Okay, any questions so far? Is everyone okay with the explanation on spring mass system?
Okay.
Okay. All right. Okay, nanti lagi 10 minit kita take 5 Okay, so total energy equals to kinetic plus potential, and you already know this, kita dah discuss. This is the total energy. Remember, kita punya total energy can be 1 over 2 kx, ka squared, Pe max, right? Or it can be Ke max, punya equation, which is 1 over 2 mv max squared. Okay, so sekarang ni dia equatekan equation ni to this total energy. This is your total energy. Okay, boleh. So what happens is, this is V, not maximum Maksudnya V at any point, V at random points, right? You use this equation at random points that you don't know if it's at the hujung ataupun dekat equilibrium. Dekat tengah-tengah lah basically. This is the equation you use to find the velocity. Sebab dekat tengah-tengah kita tak tahu dia maximum ke, zero ke, kan? So this is when you use this equation. V equals to K over M A squared minus X squared. Dia berbeza sikit daripada equation tadi. This is V max. Okay, so V max kita tahu dia ada A. Yang ni V equals to A squared minus X squared. Dia ada tolak X squared tu. Sebab energi dia berkurang. Okay. Okay. Okay, so tadi tu spring mass system. Now we are moving on to simple pendulum. Okay, should I? Okay, I want to take 10 minutes now because I'm tired. Okay, let's take 10 minutes. Come back at 11:50, Okay, and then we will start this one. Come back, 11:50. Any questions, please feel free to ask, okay? Resume recording and pen. Red. No, don't want red. I want purple. Okay, so let's do our simple pendulum now. Tadi kita cakap pasal spring mass system and its energy and the frequency. We learned about the angular frequency. Omega equals to square root K over M, and then kita ada energy equation, which is E total equals to 1 over 2 mv squared plus 1 over 2 kx squared. And from that equation, you derived all your V max, your V, derive your VA, kenapa ni? Derive your V, derive your V max, and your total energy pun kita derive juga. Kita derive lah dapat equation tu. So now we are talking about a simple pendulum, and yes, we have more equations to come. So let's take a look at this guy over here. Let me zoom in first. Hello, pergi sini. Hello. Besarkan sikit. Sekejap. It's not cooperating. Okay, takat ni je lah saya dapat. Okay. So, let's do the free body diagram for this dude. So, center mass, mg, right? So, that's your mg. And this guy is your tension because it is connected to a spring, to a string. String, bukan spring. String Lepas tu, kita nak resolve dia. So, every time it moves, right? Every time it moves, it only moves in one direction, right? Like it only moves in this direction. This is the motion. Maksudnya it's not flying, bukan flying lah. It's not like bouncing up and down, right? It's not bouncing up and down. It's moving like that. It's moving like that, which means that the motion is only in this way. The motion is not here. Okay, what I meant is it's not bouncing up and down, right? Which means if it's not bouncing up and down, the tension is balanced out by some kind of force down there, right? So it is balanced by the mg. So if I resolve this, right, this is the theta. How do I know that's a theta? Kenapa macam tebal gila ni? Okay, let me use this. If that is the theta, sorry, if this is the theta from the equilibrium, this is my equilibrium point, this displacement equals to 0 there. That is my theta when I extend it, right? The theta is equal to here as well. Okay, cuba tengok gambar ni dengan gambar atas ni dengan gambar bawah ni sama. So the theta is equivalent, right? Okay, so that is your theta baru. And then because I know that is a theta, I can say this is mg cosine theta, right? Assuming this is my y-axis, it's not bouncing up and down, which means that it is in equilibrium. So I can say, okay, my net F1 equals to 0, and I have positive t, which is from the string, minus mg cosine theta, right? So it cancels out because t is equal to mg cosine theta, and because they are equal, they cancel out, it doesn't move up and down. So tak ada bouncing happening in that direction. Okay, can you ask Auntie, please? Thank you. Okay, which means that your mg punya component in this direction is not in equilibrium because it's moving, right? It's moving, it's moving, it's moving. So it's not in equilibrium. So with that in mind, your F net in that direction, in your x direction, becomes mg sine theta. Okay, so that is your F net, which is your F net in the x lah. Your net in the fx, which is in this direction because this is your y and this is your x. So your net in the fx is now mg sine theta. And that is the only force that you see happening there. T tak boleh nak resolve. T tak boleh nak resolve because dia in the y direction already, right? This is your x-axis and this is your y-axis. Okay, so T dah ada. And then your x-axis is like that. So your F net is equal to minus mg sine theta. And you know that it has motion, which means that it is equal to ma because it's not in equilibrium. Not in equilibrium. Kalau not in equilibrium, F net tak boleh equal to 0. Okay. So this gives me F net. Okay, kalau saya ikut method yang kita selalu pakai in chapter 3 and chapter forever kita pakai F net ni. F net equals to MA. Start with the condition.
Doktor,
Yep.
kenapa yang fx tu minus?
Sebab dia to the left. Tu je.
Oh, okay. Thank you.
Alright. Okay, so let me write this betul. Not in equilibrium. So if we were to solve this using the chapter 3 method, right? So net F net je lah. Net in the F, F net equals to MA. Okay, and you know that your motion is to the left, right? Tak boleh. Motion dia to the right ke to the left? Dia ada repetitive motion. Okay, let's just assume it's MA for now. Okay, so net F ada acceleration lah. And then you know that it's minus mg for now, for now. Okay, so now I can cancel out the m. So here is how you get the a minus g sine theta. And when theta is really, really small, okay, when theta is really, 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 really small, times 1000 small, sine theta can be approximated to become theta. Okay, so your equation can be A equals to minus G sine theta or A equals to minus G. Kenapa ada L pula ni? Okay, I'm missing something here. Where is the L coming from? Tiba-tiba je. Sine L. Okay, can we stick with this one first? Obviously, I did not notice this. Kejap. Where is the L coming from? Need to know. Need to get this right so that we don't confuse everyone. A minute. FL. Where is the L coming from? It's from the equilibrium. Yep.
Kalau yang tengah-tengah tu L means yang dekat tension tu L juga kan? So this same panjang, same length.
Same length. Okay, betul. Tapi oh, saya tak faham. Macam mana awak kaitkan dengan equation ni?
Kalau yang tengah-tengah tu L, kalau yang dekat tension tu pun L.
Oh, okay. Because it's a triangle. Okay, I get it now. Thank you. That is correct. Okay, sekejap nak kena buka coklat pula untuk budak ni. Nah. Okay, bye-bye. Okay, go. Okay. Sorry, I forgot that we have this triangle over here, which means that we can say, sekejap, saya buat macam mana saya nak bikin ni? Sine. Okay, if this is L, and theta is here, sine opposite over hypotenuse, right? Sine theta is opposite over hypotenuse, mg sine theta. So opposite mg sine theta over L. Okay, so now I substitute, how do I substitute this? Okay, theta is mg theta. G theta over L is sine theta. Okay, I need to derive this balik. Obviously, I'm not prepared on this one. Okay, but the equation should look like this. So, okay, the derivation part, we will cover that later. Okay, I will try to derive this using the triangle. Okay, I did not prepare on that. I'm sorry. So this is the equation. So omega is equal to G over L. G is the gravity, and L is the length. Okay, so the length of the pendulum. Okay, so if I were to look at this diagram, okay, look, the L is this guy, right? This guy. So that is your length, which means that it's just the length of the pendulum. Length of pendulum. Pendulum string lah. Okay, because the pendulum is the ball here. So length of the pendulum string is your L. G is gravity. Now my question is, what happens when G or L increases? Okay, when G increases, which means that you are not on Earth lah, because your gravity is changing, which means something, you are on a different planet, let's say. Your gravity increases. What happens to your angular frequency? If G increases, your angular frequency also increases because they are somewhat proportional. So when your G increases, your force increases, your restoring force also increases. Remember, F equals to MA, F is also equal to restoring force. So when your G increases, your F increases, your restoring force increases, maksudnya dia akan bergerak lagi laju. So your frequency increases, right? Itu logic dia lah. Okay, so that is when you are on a different planet and the gravity is increased. What happens when your length of pendulum increases? Your frequency becomes smaller. Because why? Kalau kita bayangkan pendulum, bila kita ada pendulum yang lagi panjang compared to pendulum yang pendek, okay, ni panjang lah. So this guy moves faster compared to the one that is panjang, longer, right? Pendulum yang longer akan rotate slower, slower than something that is short. Okay, you guys can try this or maybe I will demo that in next class. Okay, so string yang pendek laju, string yang panjang lambat. Lambat in terms of repetition dia. So angular frequency is depend on repetition. So bila kita ada L yang panjang, your repetition becomes slower ataupun the angular frequency it becomes slower or smaller. Okay. So from this equation, we know that omega equals to 2 pi f or equals to 2 pi over t. And you just rearrange the equation, you will get your equation for t and you will get your equation for f. Sama juga macam tadi. Yang ni untuk pendulum. Okay, untuk spring mass system. Spring mass system equation dia ialah omega equals to square root k over m. Beza K over M and G over L. So that's the difference. Okay, so on this slide, I will derive balik in your next class so that I don't stutter, tak merepek, and we save time. Okay, so a physical pendulum. Tadi kita tengok physical pendulum kalau dalam bentuk yang macam ni lah, a simple generic one, simple and generic. So that we got the equation G over L, right? G over L, capital L. And this was omega. Now, this is for the simple generic angular frequency of a pendulum. What if your pendulum was a different object? So for example, you have, macam nak cakap, apa yang benda macam ni, rupa dia. Lokomotif. Engine lah, engine train. Engine train kan dia ada macam ada bilah macam ni kan. Tak tahu korang perasan ke tak? Yang bergerak macam ni, macam ni, macam ni, macam ni. Saya tak perasan. I think ada because I've seen it before. So basically, if your pendulum is not a ball, right? It's not a generic simple ball and it has a different shape, right? It has a different shape. Shape is different. And it has repetitive motion over the same path. Over same path. So it has simple harmonic motion, even though it looks weird. So how do we calculate for its period, its frequency, or its angular frequency? So they already derived it for you. This is the equation when you have like weird shapes. What is I? I is moment of inertia, whereby you have all those equations that approximates for different shapes, right? We have cylinder, we have sphere, we have a rod, and so on. And then mg is just mg, the weight, and L is your length. Let me check back. Tadi length of pendulum, now it is the length of the whole system, I think. Sekejap saya check balik buku. If you have any questions, please feel free to ask, except for the derivation part, because I'm not prepared on that. Mana gambar tadi? Where is it? Where is it? Found it just now. And the length of, I think it's the length of the entire system. But I need to be sure. Okay. Okay, so it's the length to the center of gravity. Oh, asyik baik saya check. Length of axis of rotation to center of mass. Center of gravity, but center of mass. Length of axis of rotation to center of mass. Dalam buku ada tak modul?
Put me on.
Okay. Sekejap. Okay, jangan kacau Mami, okay? Thank you. Chapter 9. We have this equation or not? Kalau tak payah dah nak ambil tahu.
No, we don't
Ada
have it.
Oh,
Tak
okay.
ada.
Okay, that's good. Okay, so this is just for your general information then. Okay, so T for weird shapes, because it was covered in the lecture video yang unit fizik asasi keluarkan. So I thought it was in the book. So it's not. So this is just for your general info. Huh? Right, moving on. We already talked about damped oscillations. Okay, what you need to know is that, slow down baby, slow down. Okay, what you need to know is that oscillation can be repetitive over the same path from A to minus A. For damped oscillation, the A reduces, okay, over time. So the amplitude becomes smaller and smaller and smaller over time. Yeah. Okay, I'm back. Sorry for the distraction as always. Work from home is something. Okay. So damp oscillation, tak payah tengok example. Okay, I'm going to compress all your problem solving dalam satu slide nanti, satu lecture nanti. Okay, let's summarize what we have learned so far. Okay. Okay, can you guys please help me for the spring mass system? Kita ada apa? Kejap saya nak buang ni. Let's do this together, okay? To solidify the info that you got from me just now. So we have a spring mass system. Okay, so we have omega, we have energy, and then we also have pendulum system. What is the omega? And did we talk about energy in pendulum? No, we did not. So that's good. So senang sikit hidup. Apa lagi? So omega is equal to K over M. K is the spring constant and M is your mass. That is the square root. E total, always conserved. Always. Always, E total is always conserved. Maksudnya, the total energy does not ever change. E total is the same at all times, which means that we can say that E equals to 1 over 2 mv squared plus 1 over 2 kx squared, which is also equal to 1 over 2 mv max squared, which is also equal to 1 over 2 ka squared, right? And from this equation, we could solve for V max equals to something something, which I don't remember, and V equals to something something, okay? Please memorize if you don't want to derive. For me, I will always derive, okay, unless it's too complicated. Okay, so I like this equation. So I will use this equation to derive my equations if I were you. Okay, and what else? From this equation, alamak, ketengah saving pula. Whoa, what happened? Okay.
Doktor,
Yep.
for the previous equation about V mass and V kan ada dua equation kan?
Dua? Vmax ada satu, V ada
For
satu
the
kan?
V max and V yang ada A squared minus X squared.
Yang ni ke equation dia?
Yes, yang lagi satu tu
A
K over
squared
M.
minus X squared kan?
Yes.
Ya, tak ingat. Kenapa dengan equation ni?
What's the difference for both equation?
Okay, sekejap betul. That is a good question. Vmax is KMA and then you have your V K over M A squared. Oh, dia punya square root kat tempat lain. Okay. Asyik baik cek. This guy gets the square root. Okay, so someone asked me, saya tak perasan siapa yang tanya. Sorry. K over M. Sorry, we have two equations, satu Vmax, satu V, kan? Okay, so A squared minus X squared square root of that. Alright. So Vmax, I told you before, yang spring kita ni, dia ada tempat-tempat yang dia ada maximum kinetic energy and zero kinetic energy. When it reaches the maximum amplitude, right? This is when PE is maximum and KE is equal to 0, right? And then bila dia sampai dekat negative A, okay, semua ni ada spring tau. Semua ni ada spring. It just oscillates back and forth between compression and stretching. At this point, the PE becomes maximum kat compression and KE equals to 0. Dekat equilibrium, bila dia patah balik bila dia patah balik, bukan bila kita tak buat apa-apa lagi, bila dia patah balik to equilibrium where X equals to 0, this is X equals to A, this is X equals to minus A. When X equals to 0, your PE is 0, KE is maximum, right? Okay, so to Vmax punya equation ni, let me use a different color. Vmax punya equation ni is to use at this point. Okay, so that is when you use your Vmax. Sebab kat situ KE is maximum, KE is 1 over 2 mv squared. So you know that you have to use your Vmax to find the maximum kinetic energy. Now, when do you use V? V is when you don't know where your spring is. Maksudnya bila dia oscillate back and forth, back and forth, back and forth, dia akan tiba-tiba kita stopkan dia. Contohnya saya ambil gambar dia cik, contoh kan. Lepas tu dia stop dekat this point. It's not at the equilibrium. It's also not at A. It is at this point. So macam mana saya nak tahu velocity dia kalau dia bukan dekat maximum amplitude ataupun bukan dekat equilibrium? This is when I use this equation to find out. This is when I use this equation to find out what is the velocity at some random point yang bukan dekat maximum displacement, yang bukan dekat equilibrium. I use this equation V. Faham tak?
Okay, faham betul.
Okay.
Thank you.
Okay, you're welcome. So please take note yang square root untuk Vmax ni dekat KM dia, which is sama macam this guy over here. But for your V, betul ke? KM dia tak ada square root, lepas tu dia square root A squared minus X squared.
Dalam buku ada square root.
Square root semua.
Oh, dia square root semua. Sekejap Kenapa macam tu terbalik? What page is that? Tahu tak?
111.
100 and?
7.
Oh, cacat lah slide ni. Okay, sorry Nasib baik korang, saya tanya. Nasib baik korang check. Okay. Giving credit where it's due. Okay, kejap saya erase before dia jadi perkara jahiliah kat sini. Square root pula. Bracket and square. Okay, baik. So the square root ada untuk both So km squared, A ni tak ada squared. Square root the whole thing, km A squared minus X squared. Okay, so yang ni, this guy is supposed to be A squared. Kalau nak ingat lagi senang, A squared, square root the whole thing. Sama je. This guy ada minus X squared. Okay, so that's the difference. Okay. Patutlah macam pelik. Okay, so that's good. We found out that that's wrong. Which is always good in my opinion. Okay, so apa lagi? So that's a spring mass system. Let's talk about the pendulum pula yang saya tak berjaya nak derive. New slide. Saya bitter kejap. Saya tak perasan saya kena derive. Okay, so let's talk about the pendulum. Pendulum system is also a simple harmonic motion, repetitive over the same path, right? So we have this tick-tock, like that. It goes back and forth. The equation for omega is G over L, okay, square root of that. L is the length of pendulum, G is gravity. Pendulum string pendulum, okay, same. This is gravity, okay. This is your angular frequency or speed. If they say angular frequency in your problem, it also means angular speed. So the units is radians per second. Okay, so please use your SI units for G and also for L. What else? We also discovered that pendulum ni ada macam-macam shape and there's a specific equation for that and it's not in the book. So just take note on that. It will depend on the moment of inertia. Apa lagi? Okay, damped oscillation. What is damped oscillation? It is basically oscillation, right? Oscillation, but with reduced amplitude over time. So that is damped oscillation. Oopsie, can't spell now. Okay, damped oscillation is oscillation, but with reduced amplitude over time. Apa lagi? Equations yang kita kena tahu. Okay, what is the condition for force? Condition for force for simple harmonic motion must be proportional to displacement and must be opposite to displacement, opposite direction to displacement. What is the equation that best describes this? F equals to minus kx. It's opposite to displacement and it is also proportional to the displacement. Okay, ini proportional. The force is proportional to displacement. Ini the direction is opposite. Ini ada kataan direction. Okay, I think that's it. Okay lah. So far kita dah summarize for this, the first part of this chapter. No, the two parts of this chapter. So now we are going into mechanical wave. So traveling pulse. A disturbance travel in a medium is called a traveling pulse. So sini, this is me. No, this is not me. This is me. I'm wearing a skirt here. I push this guy because I'm feeling mean today. I push this guy and this guy pushes the other guy and the other guy pushes the other guy. So we are distributing the pushing energy. Faham tak? So what travel? The pushing energy travels. But we are not traveling. Pushing energy travels. But we are not traveling. Somehow that pushing disturbance managed to reach to the end. Okay, sebab tengah buat apa? Team building. What do you call it? Kalau korang punya sekolah punya apa? Panggil camping. Apa camping?
Ice breaking.
Ice breaking, yes. Benda tu lah, I hate it. Okay, oh sorry, tak patut cakap macam tu. Okay, I don't like ice breaking basically. But when I push this guy has to push the other guy and sampai hujung sana kan. So and then suddenly it reaches the end person. So that is called, basically we are imitating a traveling pulse or we are imitating wave. What happens? It is oscillating and it is also moving. It is oscillating, maksudnya be repetitive, and it is also moving forward. So that is called a wave, right? It's repetitive but moving forward. Tadi oscillation repetitive over the same path. Now it's repetitive but moving forward. Okay, so macam ombak lah. Okay, so here, this is a different type. Alamak, I'm saving. What time is it? 12:20. So this is a different type of wave. This is a different type of wave. Basically, ada orang push, but energy goes towards the end. But the particles only moves a little bit saja, moves macam goyang-goyang sikit je, goyang-goyang manja macam tu. Okay, it's still a wave, right? Because it travels the energy. The energy travels forward. and ada pergerakan yang repetitif. Okay, sama juga macam ni. Pergerakan yang repetitif, energy moves forward. Okay, so those are the different types. Okay, I don't like this example. Let's not do it. Okay, so this is also the type of wave. Okay, so tadi kita tengok wave tu dia up and down, up and down, up and down, right? We also have to the right, to the left, to the right, to the left, to the right, to the left. That is also repetition. To the right, to the left, upward and downwards. So there's a name for this, right and left and up and down punya type of wave. So it's called, lemak dia tak panggil lagi. So I will tell you that this is called longitudinal. Okay, longitudinal. It's not longitudinal, it's longitudinal. Longitudinal, okay? So apa yang berlaku? The particles moves left and right, left and right, left and right while they transmit the energy. So the energy moves forward, but the particles only move left and right repetitively. So energy travels forward, but the particles are still here. The particles are just sikit-sikit je kat situ. Okay, so sama juga bila kita, I don't know what this is called, but when you think kan dia ada vibration. So apa yang vibrate kat sini? What is the vibrating? The air is vibrating. The air does not move. There's no wind when you do that. When you think, tak ada. Tiba-tiba ada angin kan? Tak ada. That's like spooky. So when you do think, there's vibration. You can feel the vibration. What is happening is that the air is vibrating, but it's not moving. The air is vibrating and transmit the energy. So energy moves forward. What is moving? The energy moves forward, but the air particles only goyang-goyang sikit je. Okay, so that is the wave. Right. Okay, moving on. So always result from a disturbance. So tadi kita tengok when I push this guy, he transmit the pushing energy. When we like ting, terus ada disturbance juga. When we push, the red thing pushes the particles dalam apa benda ni, glass jar ke apa ke, that's also a disturbance. We need to disturb a medium in order to travel the energy, in order for the energy to travel forward. Kalau tak ada disturbance, there will not be any energy to travel, right? Because kita yang supply that energy. Kalau tak ada disturbance, there's no energy to transmit. So the disturbance are propagated in some medium. The motion of the disturbance are associated with the transport of energy. Okay, we have seen this. Mechanical wave is the transfer of energy. So you are transferring energy, you are moving the energy without an accompanying transfer of matter. Maksudnya matter tu is still there, it's not moving. It's only moving like repetitively at the same place, right? Okay, so energy travels, not the medium particles. So here kita tengok this yellow guy. As we are transmitting the energy, as we are transmitting the disturbance, we can see that the yellow guy, dia pusing-pusing kat sini je. Okay, so that is what it means when the particle does not travel. It only oscillates around its center, around its place lah. Okay, so we have two types of waves. It's called transverse. The first one is called transverse. The second one is called longitudinal. I told you before. So transverse is when the particle goes up and down. Okay, the particles goes up and down, but the energy goes forward. This is the direction of energy. So maksudnya the energy is perpendicular to the motion of the particles. So these two are perpendicular. What's the symbol for perpendicular? This guy. Okay, up and down. The motion of the particle is perpendicular to energy. You gross, ada snake. So sini boleh nampak macam wave jugalah. I don't like that example. It's not repetitive. Okay. Next, where is longitudinal? Okay, longitudinal wave. The elements of the medium undergoes displacements parallel to the motion of the wave. So it's going right and left. Right, and it is parallel to the energy punya direction. So apa yang berlaku kat sini, kita compress. Lepas tu dia travel, compress, dia travel lah. Kita boleh nampak bila kita buat macam tu, bila kita tolak spring tu, that compression travels. Okay, so that is what happens when we do that to a spring. So ada tak gambar yang sesuai? Okay, like this one. So imagine this is a spring. When you push it, oh, this does not look like a spring. Mana yang sesuai? Sekejap. This is spring yang biasa. Kalau kita buat macam tu, it becomes transverse. Kalau kita push ke depan tu, saya tak ada contoh yang sesuai. Yang ni lah kot, but it's not really. Korang faham tak macam mana? Pernah buat kan? Mesti pernah buat. This one. Yay, we have one. Okay. So, when I push, okay, this is me pushing. Pushing. Yang bola-bola merah tu is, dia nak tunjuk kat korang particle of the spring So the particle of the spring goes right and back, right and left, right and left, right and left. And this happens over the spring as the energy travels forward. Okay, so that is longitudinal. The motion of the particles is parallel to the direction of energy. Transverse wave, the motion of the particle is perpendicular to the motion of the energy. So those are the two different types of waves. So let's write that down so that we don't forget it. Transverse, perpendicular, longitudinal, parallel. Okay. Okay, so here is, we want to look at our wave and determine what is the amplitude, what is the wavelength. Kita nak belajar lah dia punya terms of a wave. So previously we have seen this type of oscillation for your SHM graph, right? You've seen this before in your graph. Now this is happening in real life. So what is the amplitude? What is the wavelength? So the amplitude is the maximum displacement. It's still the same thing. Maximum displacement of a string above the equilibrium position. Now imagine this as your axis. This is your x-axis, and this is your y-axis, right? And this guy becomes your A. This guy becomes your minus A. So A is your amplitude or the maximum displacement. And then we have also learned in SHM what is one period. One period happens when the wave, when the plot becomes, it starts to repeat itself, right? So in this situation, it starts to repeat itself. Kat mana? Sini. Sini, kat sini. Betul? Betul, yes. So it starts to repeat itself here. So this is identical to this guy. So repetition lah. So this is one cycle. This is one cycle. One cycle is equal to, one cycle happens over one period, and one cycle happens, one cycle is also called wavelength. Wavelength. Okay, so let me erase this so I can draw this nicely. Okay. So kita buat balik axis tu. This is our, cantiknya. Cantik langsung. Okay, so this is your x-axis. This is your y-axis. And I told you this is your A. This is your minus A. And this is when you have T, one period or one cycle. And then sama juga kat sini. This is when you have 2T, two cycles. And what is 1T? 1T is equivalent to one wavelength. Wavelength is when you have one cycle of wave. Or definition kat sini is the distance between two successive points that behave identically. Okay, so that's like a little complicated for a definition. So just look at the graph. When does it repeat itself? That is your wavelength. So here, kita tak boleh plot period dengan wavelength in the same axis. Why? Because wavelength is in meter. Wavelength is in meter, while period is in time, seconds, right? So tak boleh lah pakai in the same axis. So if we want to plot wavelength in graph, sekejap tengah saving pula. your x-axis should be in wavelength wavelength in meters. So it should be like this. So time and wavelength tak boleh in the same axis, but one period is equal to one wavelength. Okay, so let me write that down. One period is one cycle, or when it starts to repeat itself. When it starts to repeat itself. Okay, as I told you before, kat sini they start to repeat, identical. Okay, and this is also equal to one wavelength. Wavelength punya Greek letter, the symbol is lambda. And the unit is in meters. That's the SI unit. Typically the unit for lambda or wavelength is in nanometers, but the SI unit is in meters. So please convert that. So nanometers is equal to times 10 to the minus 9 meter. And you have, sometimes it is in micrometer. So that is times 10 to the minus 6 meter. So please bear in mind, when they give you a wavelength in nanometer or in micrometer, please convert that to your SI unit. Okay, kejap Okay, take 2 minutes. I need to questions. Any questions so far? Is everyone okay? Okay.
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 Good. Okay, let's continue. One period is one cycle. One cycle is when it starts to repeat itself. One that is also equal to one wavelength. All right. Okay. So, okay, kat sini it starts to repeat itself. Dekat sini. 1, 2, 3. Okay, so that is your one wavelength. Okay. Saya tersilap. Dia start repeat itself dekat sini. Sekejap Repeat itself kat sini. No, bukan kat situ. Sini. Okay, sorry. Saya tersilap label. So here, dia kena sampai. Betul lah. Sekejap. Confuse-nya. Should be here. Should be here. Oh, betul lah. Betul. Okay, I'm correct. Si baik. Okay, so sorry about that. Okay, so let's talk about the frequency. We talked about lambda. We talked about lambda. One cycle, one period. Now we have frequency. Frequency is equal to 1 over t, 1 over period, right? And we have angle frequency. Okay, dah berapa ribu kali dah cakap pasal equation ni, 2 pi f. Okay, we will use this from the beginning to the end of this chapter. Okay, the haunted equation. Okay, so now we are talking about the speed of the particle. When we are talking about the speed, we are actually talking about the instantaneous speed of the particle along the y-axis, right? Particle P moves in SHM. The unit is in meter per second. What is the equation here? Good. And then we have the speed of the wave. The speed of the wave moves along the x-axis. So here kat sini kan transverse kan? This is a transverse wave. Transverse wave. Okay, so the particles moves up and down. So now it's asking you what is the speed of the particle. Kenapa saya ada masalah eja ni? Okay, of the particle when it moves up and down. So that is what the speed means. So because we are talking about the up and down of this particle at a particular time, right? So that is why we have to find the instantaneous speed of the particle. So dia macam tengok kat part yang kecil je. Let's say we are just talking at this part je. So we are talking about the instantaneous speed. Okay. Whereas the speed of the wave is to the right in the x-axis. Speed of the particle is in the y-axis. Tu perbezaan dia. This guy is in the x-axis because kita transfer the energy, so it travels to the right. Speed of waves along the x-axis is also meter per second. The units are the same. So macam mana kita nak differentiate tu? Okay. No. Okay, so sekarang kita nak cakap pasal speed of a wave. Now we are more interested to know about the speed of the wave. Speed of the particle ni instantaneous, so it doesn't, we can't, macam nak cakap, dia penting, but for this chapter we are talking about the mechanical wave. So kita nak tahu speed of mechanical wave lah. Kita tak nak tahu speed of the particle at that particular instant, right? I mean, it's not the core of this mechanical wave punya chapter lah. Okay, so the speed of a wave is dependent on the medium in which it is travelling. Okay, of course, contohnya saya ada air, right? This is my cawan, and I have water inside here, and then I have light coming in, and my light bends, right? My light bends due to refraction. Light, ni light. When dia enter from air to water pun dia dah berubah kelajuan. That is why dia ada bending, right? Dia berubah kelajuan. Sama juga macam wave. The speed of a wave is dependent on the medium in which it is travelling. So kalau sometimes it is travelling faster in a medium, sometimes it is travelling slower in a particular medium. So here, the velocity is, yang ni dia cakap speed dia tinggi lah. Speed dia tinggi. Yang ni speed dia rendah. Okay. Because, kenapa saya padam tu? Silap padam. Because why? Because you have more lambda. Sorry, you have, your lambda is greater. Okay, lambda ni kan meter kan? Lambda is greater over the time taken. So the time taken kat sini kita buat constant. 2 seconds of propagation in the medium. 2 seconds of propagation in this medium as well. Lambda kat sini kecil. Lambda kat sini besar. Okay, lambda is meter. Lambda is meter. So kita tahu V is, speed is meter per time. So if my lambda is greater, right, because it is a meter, if my lambda is greater, which means that my speed is also greater because I am traveling at more distance over time. I am traveling more distance over time, which means that my speed is greater. So when my lambda is great, my speed is great. Okay, when my lambda is great, when my lambda is long, my speed is banyak. My speed is greater lah. Okay, my speed is laju. What is laju? My speed is high. Okay, boleh lah. Vice versa. If my lambda is small, V is small. That's one thing. Okay. The speed of a wave is given as V equals to frequency times lambda. Okay, it is derived from the basic speed equation, distance over time. Okay, betul. Because speed is distance, displacement over time, right? And displacement is in meter. This guy is in second. Your lambda is in meter. Your period is in seconds. So V equals to F lambda because F equals to 1 over T. Itu je lah. Okay, lagi senang nak hafal ni lah, tak payahlah derive. V equals to F lambda. I don't know why PowerPoint keeps doing this. Hello, cepat sikit. Okay, so this is your equation. Speed of a wave. Bukan speed of particle, speed of wave. Okay, it's dependent on the frequency and lambda. Lambda is in meters, frequency is in over time, over seconds or hertz. Okay, so when a traveling wave reaches a boundary, maksudnya, what is boundary? Boundary tu macam limit lah, okay? So I have two medium. This is medium A, this is medium B. Tempat A dengan B bertemu ni is called the boundary. Okay, that is what boundary means. Okay, so boundary between medium A and medium B. When a traveling wave reaches a boundary of different media, part of it is reflected and part of it is transmitted. Okay, so let's say saya transmit a wave, right? Sorry, dia kena masuk dalam ni dulu. So saya tak boleh lah transmit pada sini sebab ini dah medium lain. So let's say the wave is already inside lah. Okay, we will not care what is outside. So I am transmitting a wave in medium A. What happens at this point? It is transmitted but the amplitude reduces. Dia jadi kecil. The energy is lost or no, the energy is not lost. Betul, energy is lost because some of it is reflected. Okay, reflected. Macam mana dia reflect? Dia akan reflect dekat same axis. Okay, silap, ni bukan axis dia. Dia akan reflect dekat same axis. So how does it look like? Let me besarkan this. So let me use pink. So dia akan reflected. If my B is denser, if B is denser, maksudnya dia lagi tumpat, denser than A. I believe tumpat is denser. If B is denser than A, then my reflection will be inverted. Okay, so macam mana kita nak invert ni? Invert. Dia akan terbalik lah dengan apa yang kita transmit. That is if B is denser. If B is less dense than A, dia akan patah balik tapi sama. So patah balik tapi sama lah. Okay, so just copy this lah. Okay, so let's not do that. Okay, so if B is denser than A, dia akan patah balik, reflection dia akan terbalik. Okay, terbalik. So see here, is this a denser or is this less dense or denser? Okay, let's see. Is this less dense or denser? Medium. Okay, ni B, yang ni A. Is B denser than A? Okay, look at this. Is B denser than A? Oh, tak ada reflection pun yang ni. Sorry. This is transmission. Sorry. Oh, ada lah. Okay, ada. Okay, is B denser than A? Okay, soalan dah legit. Okay, come on guys, already told you. Is B denser than A?
Yeah.
Yes, sebab dia punya reflection terbalik. Okay, jadi saya tunjuk awak a whole propagating wave. Yang ni dia kasih one pulse je. So supaya senang nak faham. Okay, so here I have a wave. Okay, no, this is not a wave. This is a pulse. A pulse traveling to the right in medium A. When it reaches the boundary, some will be transmitted. Okay, let's see. It will be transmitted. Okay, reduced amplitude. Kan, dia jadi kecil kan? And this guy reflected inversely. Tulisan buruk lagi sekali. reflected inversely, which means that B is denser than A, reflected inversely. Kenapa tulisan saya teruk sangat ni tiba-tiba? Okay, next. Properties of a reflected wave. It will maintain the same wavelength. Tadi kita tengok rupa dia sama. Rupa dia sama. Tak pernah tengok sini. Rupa dia akan sama. Dia punya wavelength lambda, dia punya size meter tu sama. Okay, in meter. Meter dia tu sama. Frekuensi dia pun sama. And then it maintains the same speed. Apa yang berubah? The shape of the wave may be inverted or sama, depending on the direction of the wave. Okay, itu bukan. It's dependent on the medium, bukan on the direction. So low density to high density medium, and then we have high density to low density medium. Okay, this is A is low, B is high density. This is when A is high, B is low. Okay, so when A is low and B is high, it will be inversely reflected. When A is high, B is low, it will be reflected macam biasa, reflected normally. Okay, so let's see. Cepatlah reflect, lambat sangat. Okay, so it refers inversely reflected and reflected normally. Low density to high density medium, high density to low density medium. Okay, so let's recap balik . Properties of reflected wave. Semua maintain kecuali inversely ataupun dia menegak sama. Maintain semua sama. Wave is not inverted. Okay, sudah cakap pasal ni. Okay, so ni contoh. Okay, this is an example of high to low density. Okay, high, yang ni low. Okay, apa yang berlaku kat sini? We have a rope. We have a rope that is attached to this ring. Okay, apa yang berlaku is the medium A is the rope. Medium A is rope. Medium, salah nak tulis kat sini. Medium A is rope. Medium A is rope. Okay, and then medium B is actually air. Walaupun dia ikat macam ni. Medium B is air. Sebab rope ni dia ikat, tapi sebenarnya wave tu dia keluar ke air. Dia punya, okay, kalau kita ada ring kan, and then we have a rope, kita ikat kat sini. Bila kita buat macam tu, kat string tu, what happens is that the energy tu pergi ke sini. This is air. Okay, dia tak pergi dekat, memanglah dia pergi kat sini, but before dia pergi dekat tiang ni, dia pergi kat air dulu. Okay, so that is why this example is from high to low, because air is less density than the rope. The rope has higher density than air. Okay, walaupun ada tiang, but dia lalu air dulu, baru dia lalu tiang. Good, that is why it is from high to low. Okay, faham Medium A is rope, medium B is air. For this particular example, kalau masuk dalam exam, kena ingat yang ni from high density to low density Jangan tengok tiang, tengok air kat situ. Ada air between the tiang and the rope. Okay, so what happens? When I have a high density to low density, dia punya shape takkan invert. Dia akan patah balik macam biasa. Everything else maintains, right? The speed maintains, the frequency maintains, the lambda maintains the wavelength. Next, if my wave is traveling from low to high. So here kat sini, our A medium is rope. Okay, so rope. And our B medium is the wall. Kat sini tak ada air, no air. Terus sambung ke wall. B medium is wall. So obviously wall lagi denser than rope because wall keras kan, tumpat. Betul ke tumpat tu? I don't know. Okay, B medium is wall. So maksudnya sekarang ni we are Ada orang nak cakap? Low to high. This is low to high. Bila low to high, we have reflection yang invert. This is inversely reflected. Okay. So take a look at this. This is dia sampai boundary, patah balik reflection. Okay, so tadi kita cakap pasal reflection. Semua sama, speed, lambda, frekuensi sama kecuali shape dia dia akan jadi normal ataupun inverse. Properties of transmitted wave. Reduce in amplitude, reduce in wavelength, maintain same frequency, reduce in speed. So everything is reduced except the frequency. Is this in your book? I hope it is.
Yes.
Okay, ada. Yes. Page 115 So ada properties dia kat sini. So please take note, kena hafal. Selalunya dia tanya what is the properties of transmitted wave? What is the properties of reflected wave? Okay, so you have to remember. Cara nak ingat is to understand it, what happens. Okay, so if you want, you should demo this by yourself at home. Saya punya props tak cukup kat rumah. Okay, we have 5 minutes. What can I cover in 5 minutes? Okay, yang ni kita boleh cover kemudian. Okay, kita akan sampai kepada mathematical representation of this. Okay, so I'm going to cover this in next class. Next class is Friday, right? Okay, so I'll see you then. Any questions as usual, please just WhatsApp me or WhatsApp the group. We can entertain them together. We'll stop sharing now and stop recording.